I know where there's some, right here in the hall, clerk.
No, Molly, not in there. I have enough.
One of these days.
Hello, and welcome back. I've got something old and new on my bench. If you recall, I did a video series on the Zenith 10H20Z, which was housed in a H1056R cabinet. It's AM, FM mono, and phono. And this is the chassis. I restored the other chassis and got it working just fine, and it's in the cabinet. It looks beautiful, works great. This is the chassis I bought as a parts chassis, and as I said in the video, as sometimes happens when you order a parts chassis, you get a better chassis than the one you were working on in the first place. This one has its original power transformer, its original audio output transformer. And it had some work, but I was just looking at it and had it for parts in case I needed it. It turns out I didn't. And I thought, well, since I've gone through the other one, I'll just do the same thing with this one. It'll be quick and easy. And of course, it was not quick and easy. And the reason was that somebody had been in here and put a whole bunch of stuff, wrong parts. For example, this is a 50, what is that? Yeah, 4700 4.7K resistor, 2 watt resistor right here. Somebody put a 3K 10 watt in there, and it became apparent that what they were doing was just plugging in whatever they had at their bench to try to get it to work. So I ended up going back to the original schematics and tracing out all the lines to see what they'd done and fix that. But much to my delight, once I got it rewired, got it wired and the correct components in the correct places, it worked. Now this bit of business down here, which you really can't see, but under here, let me see if I can. Yeah, right here, it's dark in there. Right here I have a couple of power caps, or a couple of electrolytics, rather. I need to restuff this one electrolytic can. This one has 4 electrolytic capacitors, interestingly enough. So I'm working on that. So I put these down here to check out the radio. Don't do this unless you're, well, don't do this, period. I'm stupid, so I did it. But they're alligator clipped into where the other caps should be. So let me turn it on and give an example of how well it's working. I've got it plugged into my dim bulb tester. I'm on full power. It's on isolation. It's on the Variac. The Variac is turned up to 116 volts, which would be about, within a volt standard for 1951, which is when this chassis was first built. So I will turn the radio on and we'll give it main power. The dim bulb tester is not on. It's on full power from the dim bulb tester. And we'll see if it makes a liar of me. Oh, no.
stream to YouTube from this drone. I don't know. Is it possible?
Oh, yeah, sure.
Yeah? Okay.
Yeah.
That's lots of summer all weekend. You could
Anyway, it's working, much to my surprise. But that's not really what this video is about. This video is about the fundamentals. And I fooled myself a bit when I brought this radio up, and I'll show you why. But the fundamental that this video is about, and this will be a random and ongoing series of basics about radio repair and how radios work, more importantly for me, is how all this mess works. But I want to talk about this video about that thing over there, which you can't really see. So let me adjust the camera. My usual setup is I have an isolation transformer, a big fat isolation transformer. I have an off-the-shelf Variac that I got at Harbor Freight or someplace like that. And I have a dim bulb tester, and I have a fancied up, gussied up dim bulb tester with the addition of this box right here. And that box is based on work that Dave Tipton did on his channel. He has a very nice dim bulb tester setup, very much like this one. But this is what I wanted to talk about, was how I fooled myself with the dim bulb tester. This dim bulb tester is a, what is this? 75 watt incandescent bulb and some power switches so you can set it to full or dim bulb, and a readout that tells me how much current it's drawing. For example, this is a 9 or 10 tube radio. It draws a lot of current, almost an amp. So it's almost 100 watts just sitting here like this. So it's 115 volts. It's 903 milliamps or 0.9 amps, drawing 97.8 watts. You know, that's a nice addition, and this whole idea, as I said, I got from Dave Tipton. But what I want to talk about is not that, which is pretty fancy, but it's this thing. It's this light bulb right here. And I cannot urge you, if you don't have one of these, fine. If you don't have one of these, fine. If you don't have one of these, fine. If you're bringing up old radios, you need one of these. And I almost guarantee you can build one out of parts that you've got lying around the house, because if you take this away, all this is an outlet, a standard wall outlet, and this is a standard light bulb for the voltages we use in the United States. And all it is you're running the power from the wall through one leg of it, through the light bulb, and then to your radio. And what good does that do you? Well, this light bulb really limits the amount of current that can be drained by the radio. So if you've been working on your radio, or if you've got a new chassis and you don't know anything about it, it may have a shorted power cap. It may have, wires lying about because somebody was in there trying to do something and quit. So if you don't know anything about it, and you choose to bring it up, I don't, by the way. This is not how I approach troubleshooting radios. I'm much more conservative. But I know a lot of people like to just bring it up and see if it works. And I get that. That's kind of fun. But if you don't have one of these, which is the cheapest safety investment you can make, potentially you could blow it up. Potentially you could melt down a power transformer, the audio transformer. You could explode old electrolytic caps. You could even explode old non-electrolytic caps. This dim bulb tester limits the amount of current that radio can draw, and if it draws too much, it in essence shuts itself down, thus avoiding fires and things like that. The usual stuff. So that's what I want to talk about today, is dim bulb testers. This will be a short video because I'm going to show you how my particular dim bulb tester fooled me, because I wasn't thinking about that number right there, the 0.9 amps. almost an amp of current to drive this 10-tube radio. Let me show you something. I'm going to turn the radio off. You'll watch current drop to nothing. I'm going to set it to dim bulb. And what I've got in here is a 75 watt incandescent bulb. And let me show you what happens when you use a 75 watt incandescent bulb in a dim bulb tester with a 1 amp radio that normally draws 1 amp. Here's what happens. The bulb comes on, goes off. Let me turn this. Then it comes back on, and it gets brighter, and you think, oh no, a short, my radio has a short. Geez, what am I going to do? What am I going to do? And you'll notice, I'll turn the volume up on the radio almost all the way. You get a little bit of noise, but that's it. And the culprit for all of this is right there. This bulb, the 75 watt bulb, is only allowing the radio to draw half an amp. Not enough. And it's dropped the voltage that's going into the radio chassis to 65 volts. So what does that mean? Well, that means this is the wrong wattage of light bulb. If you're only working on All-American 5s, they draw, somewhere between a 1/4 amp and 1/3 of an amp, something like that. And the 75 watt bulb is just fine for that. But if you've got something that's a little beefier that draws 1 amp almost in this case, that bulb is going to make you think something is wrong when in fact it is not wrong. And we'll talk about why that is. So let's start with this. This is a standard appliance bulb, 40 watt incandescent bulb used in the United States in most refrigerators and a few other ovens, so on and so forth. It's a classic bulb. It has 2 contacts, one in the center, this ring on the outside, and those two lead to a couple of wires that come up inside there, and then the filament bridges across those 2 wires. And let's see if I can make the filament a little easier to see. Yeah. So it's a wire between 2 wires. Another way to think of it is a wire between here and here. And so if it's just a wire, it has resistance, right? Well, let's see what resistance this one is. So here's my voltmeter. I'll set it to ohms, and this should be fairly low, so I'll set it to the 200 ohm range. And again, this is the resistance of that wire that's inside this 40 watt light bulb. And it is I didn't give it long enough. Try this again. 25.8 ohms. Let's make note of that. Okay, this is the bulb from my dim bulb tester. This is the 75 watt bulb. And let's take a look at the resistance in here. See what this filament measures. It measures 14. Let's call it 14 ohms even. I'll make note of that. So we have a 40 watt light bulb, 25.8 ohms, and a 75 watt light bulb, 14 ohms. Now I know that you're familiar with this. If you aren't, you should be. This chart right here. And this is Mr. Ohm's formula. Ohm's law laid out in a nice circle here. And with this chart, we should be able to say, with the house voltage here at 122.5, we should be able to figure out what the current is flowing through the light bulb, right? So the current would be, move this over a little bit more. voltage divided by resistance would give us the number of amps that are flowing through this light bulb. So we'll do that math on a spreadsheet. Okay, here we are in the spreadsheet. Let's focus on, for this argument, because this is the bulb I'm using in my dim bulb tester, 75 watt light bulb. I just measured the household voltage, and we're getting today, it varies a volt or two, we're getting 121.6 volts AC. On the 75 watt, we measured 14 ohms of resistance. So we have a voltage, we have a DC resistance. We should be able to calculate a current right here. And as a reminder, current, according to Ohm's law, is voltage divided by resistance. So let's do that right here. Let's set the voltage at I'll just point at it, that, and we'll divide that voltage by the resistance right there. And that should give us a calculation of what this should give us, the amperage that the light bulb is drawing when it's producing 75 watts at 121.6 volts. So let's measure it. Let's take a look at what the ammeter on that, or ammeter part of that VOM will tell us when we measure the actual current flowing through the light bulb. And it's a lot less. In fact, the measured current is 0.63 amps, or 630 milliamps. So that's a pretty astounding difference from 8 amps to 0.63 amps. Now, I'll tell you, at 8 amps, it would take about 3 of those light bulbs to pop a circuit breaker in my house. Common circuit breaker is, I think, the outlet, a common outlet in your house will run about 15 amps before the circuit breaker will kick in, anything above that. So 2 or 3 of these light bulbs on a single outlet and you'd be in the dark. So what's going on? Well, I can tell you what's going on. That number right there, that 14 ohms, is not a lie, but it's really misrepresenting what happens in a light bulb. And the reason is this. That 14 ohms is actually a measurement of a tungsten, am I spelling that right? Filament. And tungsten has an odd characteristic. It's not really ohmic. It doesn't behave like a regular piece of wire. It doesn't behave like a standard resistor. It doesn't behave like you would expect it to. It's not ohmic. It can't be calculated this way because when the temperature of a tungsten wire goes up, the resistance, the DC resistance of that same wire goes up as well. So it's a very curious process. When this bulb is turned on at first, there's a big inrush of current because it is indeed 14 ohms. But as the tungsten filament heats up, its resistance goes up, thereby dropping the current considerably. So what we can do with good old Ohm's law here is we can calculate, using the values we have, a measured current and a voltage or a wattage. We can calculate what our actual resistance is. So let's do that. Let's call this one the operating resistance. This is the resistance that the bulb generates when it's in use. And the formula is R equals E, we have that, over I, or the current. And we have a measured current, we have a measured household voltage. So let's see what that does for us. I should put this here. Clear this and put the actual formula in here. So this equals 121.6 divided by 0.63, and that gives us an actual operating resistance in this bulb of 193 ohms, plus a whole bunch of spare change. So we'll call it 193. So what this bulb does, and it's unexpected, but what it does is it goes from 14 ohms cold to 193 ohms hot when it's operating. And that's one of the reasons that there are two things going on in a dim bulb tester. One is, since you're running on household voltage, it doesn't vary. You can't drag this down by putting another light bulb and another lamp in your house. It's going to stay that. It's always going to be that. The second thing going on is the behavior of tungsten filaments, where they will change their resistance from a very low value when they're cold to a value large enough to limit the current. The current could have been, had it just been a plain wire, could have been 8 amps to that light bulb. Instead, the tungsten increased its operating resistance, and we ended up with a measured current of 630 milliamps, keeping that 75 watt bulb glowing. So let's look at how a light bulb in series with a radio looks. Okay, here's a dim bulb setup. I mean, it really is as simple as this. One side of the, preferably the hot side, but one side of the line, the mains comes into the base of the light bulb, travels through the filament and out the shield, or the screw part, whatever you call that, and then goes and feeds both this side of your radio, the hot side of your radio, and that flows through the radio and comes out the other side and completes the circuit. Now here's the deal. A radio has a resistance as well. It's kind of a virtual resistance, and there are a lot of things that make it up, but when it's operating correctly, the transformer is the biggest resistor in here. The power transformer, primary side, plus whatever else you've got hanging on the primary side. But you can calculate what the virtual resistance of this is, just using Ohm's law again. When I made this, I had used the standard 115 volts, which was in use at the time this radio was made. But it's about 115 volts. It draws about 1 amp, and so its virtual resistance is 115 ohms. Over here, we have a tungsten bulb whose resistance climbs from 14 ohms at turn on to 193 ohms when it gets hot. So what we have here is a 193 ohm resistor in series with a 115 ohm resistor. And therefore, the amount of current that can flow through here is limited by the light bulb. You can say it's limited by both of them, and that's true. But what the reason for setting this up in the first place is to see if this is shorted. If this primary transformer on the radio chassis is shorted, or something else has gone awry and it's pulling a ton of current out the secondary side, enough to melt down the transformer and blow things up, you want to know that. So what happens is that if this is shorted, all of the current is being pulled through here, and it limits the amount of current. This tungsten, when this is shorted, let me say this a different way. When this is shorted, it's as though this wire just goes right to there and ignores all of the rest of the radio chassis. And therefore, we've seen that this will only allow about 600 milliamps to get through. It's just when it's shorted, it's 600 milliamps. When you add another resistor in series, like a radio chassis, it's less. So this is a current limiter. It's a very cheap, easy to build thing that will keep damaging current from flowing through here. If this weren't in circuit and this was shorted in some fashion, you would pull all the amperage that the outlet is capable of providing, right? About 15 amps. You'd be pushing 15 amps through your damaged radio, and I guarantee you 15 amps is enough to weld with. Some bad things would happen. This light bulb prevents that from happening. When it glows hot, that means this is close to shorted. There's something wrong in here. When this is dim, which is the ideal case, where you can barely see it, that means things are happy. The radio is happy. It's drawing a reasonable amount of current, and the bulb doesn't have to get in the way. So, why did that bulb burn brightly when I turned on the radio in dim bulb mode? That's because of this value right here. The radio is trying to pull 100 amps.
But that ain't the way I heard it.
So what it does is pull the maximum through the lamp that the lamp will provide. And if the lamp doesn't have a high enough wattage rating, it will do like it did in the example at the beginning of this video. So what you've got to do is you've got to have a wattage rating that's higher than the wattage rating of the radio. And in this case, the wattage rating of the radio is about 115 watts or 100 watts, give or take. So this is a 100 watt radio. It's a 75 watt bulb. This is going to demand more power than the bulb can provide. You might have noticed in the opening video that when I did turn it on and the bulb was bright, the operating voltage that we were actually providing to the radio was around 60 to 70 volts, way under what the radio needs to operate. That's simply because this bulb couldn't handle the amount of current that the radio needs. So what do? Well, if you've got a radio that draws 100 watts, you need more than 100 watts of light bulbs. You in fact need about 1.5 times. You need 150 to 200 watts of light bulb right here in order to do a good dim bulb test on a radio chassis. The smaller wattage in this case doesn't hurt anything. It certainly does its job. It limits the amount of current and voltage that gets to the radio chassis, but it doesn't let this get into a good enough operating mode to show you whether it's working or not. So in this case, I would add another 75 watt light bulb in series with this light bulb, and which would be in series with the radio, and that would give me enough wattage, I think, to allow enough current to drive the radio appropriately. What was I going to say about that? Oh, Electronics Old and New has a dim bulb tester that he built that's actually 4 bulbs in series, and he can turn on or off, link in or out of circuit from 1 to 4 bulbs, so that when he has a higher amperage draw, a need for more wattage on the radio side, he can shift in more bulbs and still have a reasonably functioning dim bulb tester. So I'd recommend you go take a look at his videos and watch his dim bulb tester in action. I don't recall if he did a video on designing that or not. He might have. He's done a lot of supplementary videos like that. Anyway, that's why you need a dim bulb tester. That's how a dim bulb tester works. I hope this wasn't too burdensome for you. I'll be doing more. The next one I want to do involves tank circuits. But I've got another radiator project to start, so I'll start the new radio project and think up a way to do the tank circuit one. So until next time, take care, be safe out there. See ya.